We're now going to take another look at the Bernoulli equation, and in this case we're going to be looking at an engineering application, a device called the Pitot tube, sometimes called the pitot-static tube, and this is used for velocity measurement. So what we're going to do, we're going to look at the relationship within the Bernoulli's equation. We ask ourselves the question, what happens when the velocity along a streamline comes to zero? And this is kind of important to the measurement of the pitot-static tube itself. So what I'm going to do is I'm just going to draw a thing that will look like a pitot tube. We'll show you in a moment. But this is a tube that is placed within a flow. And it is connected at the back here to a cavity, and I'll say that that is measuring PC, so pressure at C. The point here, I'll call that point B, and here we have some streamlines coming towards that tube placed in a flow. We have other streamlines going around the tube. And I'll call this point here point D, and I'll say this is P1. Now what happens is we have a thing called a stagnation streamline, and that's the streamline that I have right in the middle here. And what happens is the flow comes along, and it slows, eventually gets to this point, and it hits B, and at that point it does what we call stagnation. It stops. And consequently, we sometimes call that the stagnation streamline. But the characteristic is that the velocity at B is equal to zero. And consequently, what this pressure is measuring is what we call the total pressure in the flow. And so I'll say PB is equal to P naught. That is the way that we refer to the total pressure. And another pressure measurement that we're making here, I'm just going to assume that we have a wall over here. And this will be point A. And we'll call this a static pressure tap. And so this will be measuring what we call P infinity, or the static pressure in the flow. So with this scenario, what we're now going to do, let's take a look at Bernoulli's equation for this particular configuration. So that is Bernoulli's equation, and what we're doing, we're evaluating it between 2 points. Point A, which would be similar to point D because that is a static condition, and the other point we had was point B. So point B is where the flow is stagnating. And what we're going to do, we're going to assume that ZA is approximately equal to ZB. Not much of an elevation change, even if we're dealing with water or air. The other thing that we said is that at point B, the velocity comes to zero, and consequently at point B, the pressure being measured is P naught, or the total pressure in the flow. So with that, I will rewrite Bernoulli's equation. And remember, we said that at point B, the velocity is zero, and consequently, the velocity term is zero. And we said that that is equal to this P naught, which is what we call the total pressure. And so at this point, velocity is equal to 0. And PA, that is measuring the static pressure in the flow. It's basically a very smooth surface where you're just measuring the free stream velocity within the flow or the local velocity at that point. And so the velocity is not being hindered at all by the pressure measurement at that location. So we're measuring pressure at a location where V is equal to V local. Sometimes with P infinity, that would be V is equal to V infinity. So that would be out in an undistorted streamline. But you can also measure static pressure along a wall. So with this, what we're now going to do, we're going to try to solve for the velocity at A. And we end up with this equation here. So what does this tell us? That tells us that with Bernoulli's equation, if we are able to measure this pressure for the stagnation streamline, and if we're also able to measure PA, which was what we call the static pressure, and usually I'll show you a thing called the pitot tube next, and we do that by making a measurement at this location and knowing density of whatever fluid we're dealing with. Let's say we're dealing with air, that would be P over RT. Knowing the density of the fluid, this then enables us a way, if we can measure P naught minus PA, and if we know density, we can then solve for the velocity in air upstream of that particular location. And so that is the premise behind the Pitot tube. What we'll do in the next segment is we'll take a look at the application of this, and we'll crunch some numbers to see what types of results we get using this relationship from the pitot tube.